Hello, welcome to our project titled A Statistical Investigation of Climate Change. We are Kaya, Oyo, and Nate, three undergrads from St. Olaf College.
Our research focused on approximating the standard error of glacial melting, inspired by previous work with two glaciers, located on Volcan Chimborazo in Ecuador and Volcano Ravage in Iceland. Knowing the standard error is necessary for accurately predicting future melting of glaciers. However, new technology allowing for high-resolution measurement of glacier change has made standard statistical methods computationally intractable when computing this standard error. Our research specifically focused on comparing two methods presented by Norwegian glaciologists Cecily Rolstad for efficiently calculating the standard error of glacier melting. More specifically, we sought to address their lack of accuracy outside of certain conditions and develop evidence supporting the standardization of an accurate approximation method for a wider range of conditions. A tool that is used in Rolstad's process of approximating the standard error is a variogram, which helps one measure the semivariance between spatial points. Its parameters, nugget, sill, and range, aim to effectively quantify a terrain's unique features and are used to determine the standard error. Nugget quantifies the measurement error of the data. Sill represents half of the variance, though we will more often refer to the partial sill, or p-sill, which is the sill minus the nugget. Lastly, the range is the distance at which points are no longer considered spatially correlated. These parameters obtained from the variogram play a key role in Rolstad's methods in approximating the standard error. The final equation used by Rolstad is shown below, hereby referred to as Rolstad 1. This equation is derived from an earlier version referred to as Rolstad 2, shown in the second equation. Based on the results of our research, this is the equation we will propose as the better approximator of the standard error. To measure how changing nugget, sill, and range values affect the accuracy of the Rolstad approximation, we simulated thousands of artificial glaciers. An example terrain surface is shown in the plot below. And we analyzed how the approximation performed in comparison to the empirical standard error across a variety of parameter combinations to represent glaciers with varying characteristics.
From the simulation study, we were able to see that different features of the glacier proved to have an impact on the accuracy of the approximation methods. As demonstrated in the top plot, as nugget and sill values increase, Rolstad 1 increasingly overestimates the standard error. Additionally, the rate of nugget to sill overshadows the effects of other parameters. Ideally, we want the plot to have straight horizontal lines, demonstrating that the accuracy of the approximation would not vary with different parameter values. This plot ultimately confirmed our need for a new approximation method, one where the accuracy of the approximation does not vary significantly with changing parameter values. The Rolstad 2 estimation accounts for the nugget to sill ratio. However, looking at our second plot, we see that the accuracy of the Rolstad 2 approximation decreases as the ratio of range over area increases, more so as the perimeter of the glacier decreases, holding area constant. After analyzing both of the approximation methods, we created a plot to determine under which circumstances each method should be used. Blue areas on the plot indicate that Rolstad 1 is closer to the empirical standard error and thus should be used, whereas red values indicate that Rolstad 2 should be used. White areas indicate both equations would work equally well. Our top plot indicates that a strong case for using Rolstad 1 exists only when nugget and sill are in close proximity to each other and there is a high range to glacier area ratio. Looking back at the glaciers that motivated this research, we have compelling evidence supporting the use of Rolstad 2 on block glaciers for approximating the standard error.
The digital elevation models shown on the right are models of our two case study glaciers. They demonstrate how much ice change has occurred in different parts of the glacier over different time spans. Red areas represent glacial loss, and blue areas represent glacial gain. We applied the two approximation methods to the glaciers with the notion in mind that the second approximation method would be more accurate, according to our tile plot, as both glaciers would land in red areas. Interestingly, as summarized in the table in the middle, the Rolstad 2 approximation is lower than the Rolstad 1 in both scenarios. The Rolstad 1 approximation is commonly used by statisticians and glaciologists today. As we have two opposite extremes represented in our case study glaciers, our findings suggest that in real-world situations, Rolstad 2 in general offers a better approximation method of the standard error. This is especially the case when there is a high nugget to sill ratio because as the nugget to sill ratio increases, the overestimation of the empirical standard error by the original Rolstad approximation increases linearly. However, The accuracy of the Rolstad 2 was influenced by shape and area. We are currently investigating the relationship between perimeter, holding area constant, and the accuracy of the Rolstad 2 approximation in order to obtain an approximation method that is reliable under yet more conditions.